好什么？开始录制这样吗？
对，就是差不多先。
我懂，没问题。
觉得
Hello, 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 hello. 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 是你好，你好。
阿威，
哈维是这边对。
哎，怎么是你？
啊，我两个都是我，对吧？应该另外一边，我跟 Scott 两个吧，就是对。
太辛苦了。办一次活动，不死去到半道。
啊什么？
人家办一次活动，不死去半道。
对啊，对啊。
中午不能休息。OK。
到那个你到3楼那边，然后你跟他讲说是你们那边刚刚，OK，开上去，我是谁那边，然后我等一下，然后我就想一下，你拿到或者还没拿到？好，大概15分钟。OK。来，过来，他找去，好。
这个是，哦，sorry。Hi, Elisa. Sorry for the inconvenience. I will be handling other track, so the acting host will be the Scott, and I'm very sorry for that.
隔壁也听得到你的声音。
Sir, what kind of staff is the audience? Sorry. I really was saying that I'll be hosting our chat. Oh, all right, thank you. Sure.
怎么了？你看。对。
所以今天这两边都是
那个跟 Scott， 对不起，
那边就是最后
结束我懂，没问题。 Hey, hello, hello. Can you see me? Sorry.
Yes.
Okay, great. I was a little bit nervous because because we don't have any emergency hotline, so this is the.
Oh, I tried to message you on Telegram. I guess you didn't get it.
Oh, I see. Sorry, because I was too busy recently.
Yeah. I mean, it's probably a bit late.
Yeah, sorry.
Am I live?
Yeah, there are some people here, but because due to the camera setup, I cannot turn around my camera. But you are very welcome in Taiwan here because you know that in Taiwan, that many semiconductor and the fabless company they are not intended to open their PDKs. So in the academic field here in Taiwan, like National Taiwan University, the top grade university in Taiwan, we are very eager to know that how does the UC Berkeley CS250 to adopt this kind of open source PDK and EDAs. Yeah. And by the way, do you have any slides or do you want to do it?
I do have good slides. And I can share them.
Yeah. Okay. Then it's free for you to share the screen.
See them?
Yeah. I can.
Turn the lights on. Wait. Let me just turn the lights on in my room. You'll be able to see. Okay. Everyone see me? Good.
Yeah. Good. Oh, okay. So we're actually at a start time. So without further ado, let's welcome Aria from UC Berkeley to present us the wonderful FOSS EDA and the FOSS tool trend. Thank you.
Well, I can hear you clapping, so I assume you're there, but I can't see anyone, so this is a bit weird.
Sorry.
It's like Zoom University, right? Anyway, thank you for having me. It's nice to talk to people who are like-minded and share our experience. So I'm Arya. If I talk too fast, you can tell me to slow down. I'm from New Zealand, so we tend to mumble as well. If you need me to slow down and be more, to enunciate better, just interrupt me and let me know. But yeah, I am a PhD student at UC Berkeley. I was the TA for the first class. I think it's at least maybe one of the first classes to teach with Skywater 130 in fall 2020. And so that's like 2 years ago now. The class was pretty small. It was about 15 students. The professor was John Wojnik, who's a longtime VLSI person. And we were taking advantage in the end of this, I mean, I'm sure everyone's heard of it, but the Google and Skywater collaboration with eFabless, where Skywater open sourced their PDK and eFabless provided sort of a wrapper for all the open source ASIC tooling, and they presented this like complete RTL to GDS flow, and they're offering free shuttle runs for anyone who would submit a design. And so then we built a small FPGA and we taped out. I'll go into detail about that, but there's a lot of work, there's a lot of learning. And just as an immediate disclaimer, I want to say that this was 2 years ago, and a lot has improved since. So anyway, without further ado, a bit of background about me. I got a bachelor's degree in New Zealand, and then I worked as a software engineer for about 6 years. And then I decided to go back to grad school. And so I think this is important because I have a very software engineering mentality when it comes to hardware. I'm originally a hardware engineer, right? But I do not like crappy software, and it makes me mad. And I'm very happy to write my own. I'm much happier to write my own software than I am to use garbage software. So this is kind of part of the problem about software engineers in general, but it meant that when I got to Berkeley, I went sort of we'll get to that. When I got to Berkeley, I did chip design a different way, but we'll go through that. The course itself that we did this for, the CS250, I'll give you the introduction to that. It is a graduate level course. It's run basically every 1 or 2 years, and it's usually quite small. Like I said, we had 15 students. It's open to advanced undergraduates as well, we had 1 or 2. But usually by the time people do this course, they have prior experience in digital logic, design software. They've usually done one of the prerequisite courses, which has them do actually a pretty complex RTL design and run it through a bunch of commercial tools. But we give them like a push button flow, like we give them a make file, or we use another tool, like we have this thing called Hammer that will wrap all of the commercial tooling, and they just have to hit like make blah and it'll do it. They don't have to understand what the tools are doing, it'll just make it for them. That is really an exercise in writing RTL. So by the time they get here, they kind of know a bit about how visual design is done, and actually after that last course, that 150, 151A, they're pretty much qualified to apply for jobs in industry as like fresh out of undergraduate. So CS250, this graduate course, tries to extend that a bit. It creates these a collaborative group project environment where people apply to split up and do different projects. Usually things like accelerators or CPU cores or memory controllers. And then we get more stuff into like how to do a better design for fabrication, for like something you want to build. Although typically it doesn't actually end up getting fabricated. There's another course for that. And my research, which is also like a little bit of background for you, I do computer architecture, so I've been building open source FPGAs at the layout level. And when I first came here to school, I had to learn how to do chip design, and I was disgusted, absolutely disgusted, to learn that you have to use these really crappy, well, they're not, they do fantastic work, but these like ancient UIs for these commercial like tools that have the really thick manuals, and they only work on specific machines, and you need to have licensed servers, and someone needs to tell you what bash script to use, and there's a lot of tribal knowledge around what stuff works with what version of what tool and when, and you can basically just copy their scripts and then you like tweak them a little to get things going. We have these ancient but stable operating environments, what's the title there? And it's just, every way you can imagine it's a pain. Like if you come from like writing software, maybe in SSH, maybe over a terminal, you log into some box somewhere and you can do it from anywhere, you can do it from the beach. You can no longer do that if you're trying to build a chip. You've got to get a fast connection, you've got a remote desktop to the server in the building with the NDA, so the IP is protected, et cetera, et cetera. It's all very painful. It's like learning Microsoft Word for the first time, except you're no longer like 8 years old and you don't really care. Like it's annoying to have to learn all the different shortcuts and the two sets of tools do it differently. So long story short, I did not come to grad school to get a PhD in using vendor tools. I wanted to learn how it's all done, see if I can make it better. So when I was asked to TA CS250, and when there was this opportunity to look into Skywater 130 and OpenLane, I really jumped at it. OpenLane, I don't know what the audience's background is, but this is that eFabless suite of tools, that RTL to GDS flow. I really jumped at this because it was a way to achieve the goal, which is to build chips, without having to go through the hundreds of pages of synopsis or cadence training and like sit in the lab with other people who already knew how to do it. You could figure it out yourself. And that's what makes it such a powerful learning tool. You can really introspect each part of the RTL flow. You can see the code with your own eyes. You can see how it works, and you can try and fix it. You can run it on your personal machines. You can run it in familiar environments. You can students run it on their laptops. You don't have core limits. You can run 20 cores, 100 cores of searches at the same time. There's no licensing service. And on top of all that, there's a very active community of very responsive developers, thanks to eFabless, who will, they're very interested in having users try their stuff, and they're always listening to see what would make it better. And so, if you had a problem, they respond pretty quickly. And then the other really nice part is that once you're done, you can share every part of what you did, down to the GDS. There's no IP limits. You can just give people what you did and say, look at this, what do you think? Look, there's a transistor. And on top of that, the eFabless harness for the designs was this really neat, they called it Caravelle. It was like a design that had space in the middle, and around the outside they had the I/O pads, and they had a little RISC core and SRAMs, so that you could do bring up without having to worry about I/O, your own clock generator, your own other controllers or whatever. You could basically just put any design in and plug it into this thing and try to get it to work. That was the promise, and it made it a lot easier and a lot more tractable. So then, okay. So I'm trying to get through so we can have tough questions. But okay, so with that out of the way, how do we do this course? Well, we suggested to the class that we build an FPGA, and pretty much everyone was like, okay, that's fine. I don't think anyone had a better idea. So I got to pursue my research interests through this course. And we had some initial lectures on FPGA design, like stuff you'd read out of the textbook straight away. And then we had some follow-up lectures on VLSI topics, a review of circuits. This is stuff that I should have covered by now, but we've reviewed it anyway, like MOS models, power, parasitics, pulse distribution, etc. And we talked a bit about like common blocks, like how SRAMs are made, how muxes are made. And then we basically split them up into groups and gave them a little task each, which I'll go into. And then we had regular meetings to discuss progress, share advice, learnings, whatever. We all collaborated in real time over Slack, which was really important because as students, they were usually awake early in the morning, meaning they didn't go to bed, and any normal regular communication would sort of fail, so I'd be awake at like 10, 11 p.m. and then suddenly stuff would start happening and then I'd have to like help, figure out what they're doing. We share what we learned. We put all the code on GitHub. We enforced a style guide so that people could share and read each other's code. And that helped people jump from one project to another as they had time. And then ultimately the assessment was based on sort of contribution to the work, both as by their own admission through personal statements and as judged by our professor. And so then what were the groups? We took a typical FPGA fabric and we said here are the parts. The parts are like we had configurable logic blocks. That's the thing with the lookup tables and registers. There's a configuration element, like how do these blocks get configured? Where does that configuration come from? There's the interconnect between all the configurable logic blocks and the SRAMs and the next thing which I'll talk about. So there was the SRAM block. We needed memories basically. And this ended up being, we didn't ask students to write their own SRAM compiler. Luckily there's OpenRAM. So we asked them to write a wrapper for OpenRAM that would automatically, or basically present a unified interface for our FPGA to an OpenRAM SRAM block. And then of course a multiply accumulate unit, which is like a configurable with multiplier and accumulator. And then there was like one other team that was in charge of bringing these all together and tiling them and making sure they all worked. Each team, importantly, had to use the flow basically to harden their own macro, like they did the RTL to GDS flow on their RTL, they tested it, they optimized it, they had to iterate on it to make sure it was as dense as possible and sort of had the interface it needed. And then they passed it up to the integration team and we combined those together. We reserved layers of the metal stack for power, routing, ground, clock, and interconnect at the top. And then we said, okay, your team can use the bottom 3 layers, like the local interconnect layer and 2 layers above that to do whatever you need to do. And so that helped people kind of work independently. So we divided and conquered. I just want to check that everyone is hearing me okay, because I had no feedback.
Yeah, actually, 就是讲者现在想确定一下，说这边的大家的有没有什么特别想问的嘛？他想说真的先暂停一下。还好吗 ？Okay, everyone's just satisfying with your talk, so we can just keep coming, and that will be fine.
I hear it.
Okay. Oops, sorry. Can you hear me now? Oh, sorry, I muted the sorry. Everyone here, I just asked around the audience here, that is, everyone okay with your talk? They said yes, they're completely okay with your talk, and please go on.
Okay, cool, great. Cool. We'll keep going. So we split it up and we handed out different components, and then we said to students, please go away and do this. To start you off, I prepared an introductory lab, which is where I said here is an example piece of RTL. We're going to run it through all the open source tools that we're going to generate the final products, the GDS, etc. And that got them familiar with the prerequisites. They got them set up with their environments, like on their laptops or whatever machine they needed to use. If they didn't have a machine, we gave them a lab machine. They learned some Tickle, which it turns out is pervasive in this space. So they learned some Tickle. And then, we basically were available. I was always listening over Slack. Everyone was sharing problems there. We'd share, some person would figure something out and then share. I try and be one step ahead, so I try and try everything once, and then everything I run into I tell them. We also actively participated in the open lane / the Skywater Slack, which was really nice because the developers were right there. As I said, we shared work through GitHub. Some students ended up doing custom layout using Magic. So we had one of our interconnects had a transmission gate. We used, as I said, OpenRAM for the SRAM blocks, and then we had to integrate this with an FPGA tool chain. So we used the open source GeoSys and the XPNR for the FPGA tool chain. It was all free. One asterisk. It was all free except one time thing. And they did it. It was incredible. They came out with this FPGA. It had these CLBs made of 4 S4 LUTs, which are like an exotic LUT topology. The interconnect was a bunch of switch boxes and connection boxes that they connected their neighbors, like north, east, southwest. The Mac unit was configurable and worked. Everything was functionally tested with like an RTL test bench. We had various SRAM sizes in the wrapper block. We built the bitstream generator for this thing. It was like hierarchical, so we asked each team to build the bitstream generator for their block, and then a top-level Python script would combine them all and generate the whole thing, depending on where it was put in the layout. It was really cool. The first attempt we had at putting it all together was kind of disastrous. Here we have 4x3, so we got all of 12 of these things on this die. We didn't really know how to use the tools well. We hit a lot of bugs. It was very hard to get density up. Like, we had a lot of problems with congestion, density limits, and it was like there was basically no space for other macros at this point. And then a really interesting thing happened. The students took it upon themselves to make it better because they were so close to the end and they just wanted to optimize it, right? Everyone decided they'd have a go at like running this tool and tweaking the parameters to see, what should the target density be, what should the core utilization be for each block, what if we take the macros out, and they all sort of went away and they would constantly be competing basically over who had the most dense design today. And without me having to do much, we got up to here. I think it was a few heroic students that did most of this, but we went from 4x3 to 8x7 in the same space. And that's just by figuring out how the tools work better and what their limits are. Of course, today this is called, a hyperparameter search, and you use machine learning of some kind to search the space for you. But we just had grad students and undergrads, so effectively the same. So this was the final product, and it was incredible. But those you can immediately see some problems. Like, where are the S-frames? Where are the multiplied cumulants? Well, they're not there because we had a bunch of problems. The first real problem we had was, we couldn't map ledges. We had to go create a mapping for GeoSys that wasn't part of the PDK at the time. That was annoying, but we did it. We had to make an exceptional, we had to hack the open lane scripts up to allow for faultless designs. The open source simulators don't support transmission gate like the high impedance state, Z. So we had to use Synopsys VCS, which is the asterisk I mentioned before. It's the only non-free tool we can use, and it's sort of dirty. In our defense, we could have made the whole thing without the transmission gate, and then it would have been completely free. But in this case, it was nice to be able to also do the custom layout. So as I also mentioned, the flow would often fail with density and congestion issues, and so tweaking these target parameters was very difficult. It's not like, how to put it, the input is a number, and you don't know what that number means until you read the algorithm that uses it. And not everyone wants to do that. So for most people, it was a question of, I need a number in a range that works, and the only way to find that range is to just run a sweep of all the values. And for every little change in the input, this range would change, so we did a lot of iteration. Of course, I've since learned that this is what people will do in industry anyway, and it seems to be de rigueur. So I guess that's not really a problem, it's just life in building chips. On top of that, the power delivery network didn't work. I had to go in and manually measure the things and decide where the tracks should go. It's stuff like this, like the clock tree synthesis would break for large macros because the placement tool couldn't figure out how to move the buffers around the giant macros. So we just ditched the clock tree, and we probably had a lot of clock skew as a result. The SRAM blocks, they didn't end up being available in time, so we had to drop those. I think there was one available, but it was too big. So then the SRAM block on the FPGA would be too big, and so we just had to drop it. Likewise, the Mac, because it's just a big thing, it's like, unless we did like an 8x8 or like 8-bit inputs, it would have been too big, so we ended up just dropping that too, just to get something out the door. And then lastly, and probably most importantly, the verification tools are very incomplete. They are like, and it's not because, well, I think at the time it was because a lot of the timing information or the power models were available, but they weren't quite open source yet, I think, if I recall correctly, that I may be wrong on that. But either way, we didn't have access to a tool that would let us do design like handoff completely. And so we just had to, and we didn't want to resort to using the commercial tools, so we just said, okay, we'll get it to the state that EPABLess wants, which is like the following DRC errors are okay. And they were things that they were aware of, and then we just handed it over, and we were done. So that's all very negative. The thing that saved the day was, again, this very supportive and responsive development community, which is exactly why you choose open source. They were very helpful over Slack. They're really interested in hearing what our problems were, and they responded within 24 hours. Working on the OpenLink code base was reasonably straightforward. We were able to fix code ourselves and submit bug reports or just submit fixes. And actually, since that time, I think most of these issues, if not all of them, have been fixed, which is great. And that's why we believe in open source so much. So, in conclusion, we did it. We submitted this class in 3 months, built this FPGA, and we submitted it to MPW1, which is the multi-project wafer. It was fabricated and delivered to us a year later, by which point all the students had left, and I was too busy. So I have a stack of them over there, but I haven't pulled them up. There was actually like a bug too in the harness, but that didn't matter because the class was a success. We knew that using this open source stuff that was brand new was going to be risky, and you know it was basically as painful as we expected, but with sort of enough motivation, with enough curiosity, we could dig into every problem. The thing that I liked about this, that I hate about doing commercial tools, is if I hit a problem with a commercial tool, I have to contact an application engineer to the support channels of that tool, like the vendor using the support contract that whatever institution I'm at has. I have to wait weeks, I end up in meetings, it takes time, nothing gets done. But here I could just read the code until I figured it out. And that happened a few times. And so we went from a vague awareness of VLSI design tools and finding what each step does, to really knowing them well enough to help write our own. And I think the proof was in the fact that the students were all engaged and they all felt accomplished. And I mean, I myself learned a lot. So that was really cool. By way of comparison, actually, in that same run, the state-of-the-art OpenFPGA compiler at the time, which is this thing called FPGA in Utah, University of Utah, someone was designing a chip using that tool. And what that is it's basically the same thing. It's a very similar design. You can see it's like a tile of these configurable logic blocks. But they use a cadence tool to I think do this synthesis placement and routing. So they've got a much more dense configurable logic blocks.
Oh, so they're using the cadence tool. I think that they use the SOFA, the Skywater open source FPGA, but so you're saying that they're not actually using the FOSS tool to do the fabrication?
No. So they did a mix, right? They generated these blocks. I mean, it may be a different one. I think there were a few FPGAs in there, but this is the one I knew about. They generated each CLB with the cadence tool, and then they tiled them, and then I think they tiled them with the free tool, and they put them into the free tool to submit it. But sort of the core block was done with that, and they also did things like customize each block with a different part of the clock tree, so that the clock tree was embedded, and that because that tool lets you make each of these CLBs different. You can slightly tweak them to have a different clock buffer or whatever you need. And so this is a bunch more experiences behind this tool. This is like state of the art, and we got into the same ballpark with 7 teams of about 2 students in 3 months, and I think that was really nice for the students to see. Clearly not better, but it's like to even be at that level, I was really impressed. Other lessons, I think I've kind of beating the bush about, but basically it may be rough around the edges, but it is all absolutely worth doing. A lot of the students really liked playing with the tools and not just using them, and because a lot of people, especially engineers, right, will learn by doing. It is much easier to say, here's the script that runs, you can see what each part does, tweak it until the thing works, than here's a makefile, good luck. We don't know what this block does, or this binary, or whatever, we don't know what's going on here. Yeah, so that was really cool. And as for what's next, I think I was really excited at the time to sort of turn this into a shared open source course based on Skywater 130. But it turned out to be very hard to keep up with the software changes by myself. It really needed like a community that would be constantly changing it, and you know, almost with these like software engineering practices. If we change the API, if we change the flow, if we change the configuration parameter, we've got to change the course where we teach how to use it. Maybe it's part of the continuous integration. It was kind of too early, I think, in spring 2021 to do that, but maybe now there's more appetite to develop a shared course. Another interesting thing is that there's this takeout class at Berkeley, which is sort of more aggressive, has a broader scope. They tend to build like a radio chip with a processor on it. Like they have an analog front end, and they have like a RISC core or something on there. And they typically will tape out with commercial tools because they'll have very experienced grad students come and like tell them this is exactly what you need to do, and here's like you do this bit, we'll put it together, we'll tape it out. They were considering Skywater 130 adoption. I don't think it was mature enough for them in 2021, but I think they're still thinking about it. And I think if we can get a course like that to use Skywater 130, then that's a huge boon because they really care about the big tick at the end when LVS is clean, DRC is clean, and all the timing passes and like across all the corners. So yeah, I think that's sort of the next step for like a more advanced course.
Oh shit.
This, of course, everyone in the open source community. These tools are, they take a lot of basically volunteer hours, and we're grateful for them. And also very responsive people.
Sorry,
and yeah, questions?
Can we go back to 1 or 2 pages? Next page, sorry. Yeah, this one, because we're having a little connection outbreak, so can you just kind of replay these 2 kind of slides? I'm so sorry.
Oh, here, sorry. Yeah, this speaking fast again. These are the students in the class, and I want to thank them. I'm not going to name them each, but there's 4 credit words due. These are the people who did it. And on this slide, I wanted to acknowledge that like all of this work was built on a lot of volunteer work by members of the open source community. Of course, Google for its funding of Skywater and Fables to do this. OpenRAN, KLab, a lot of the other stuff we take for granted. Tim Edwards especially has he's taken on the maintenance of a lot of old VLSI tools like Magic. And a lot of the developers involved were very helpful. They really kind of held our hand through bits of it, and we all helped each other, right? Like we helped them pipe clean this process and try and get it done, and like see what the rough edges are, and they helped us learn a lot. So it was really cool. Yeah, questions?
So, 请问是博明先生吗？李博明还是不是？在场有想要问问题的吗 ？Okay, we're having a live one here, so I'm passing the mic here.
Okay.
So, yes, thank you for your talk. I want to ask during your case, do you face any bugs in the software? Because in my experience, I think the open source tool has a lot of limitation and some issue. And also in the verification, I think the difficulty of the verification is that you need a lot of domain knowledge, like the RC, how to extract them, and it's tightly related to the hardware behavior. So in software level, we don't know this kind of domain knowledge. So how do we come with this kind of problem in open source tool?
So the first question, did we find bugs? Yes, we absolutely found a lot of bugs. I mentioned them. They are, oh. Yeah, some of the bugs were, just features that hadn't been added, so they weren't really bugs, they were just things that were missing, like, for example, not having clocks. But then, every now and then, we'd hit, like, a state fault in, like, the router, or the placer or something, and then that's when we'd say, hey, developers, we hit this bug with this case. And they were very quick to respond. It'd be fixed within a few days. Of course, this is a benefit of being one of the first people and everyone being very focused. Of course, I don't think that necessarily scales, but I still think the turnaround when you hit a bug in the open source tools, like with the current community, is faster than if you hit it with the commercial tools. Admittedly, the commercial tools are already much more stable, but they didn't really frustrate us that much. I think the thing that frustrated us the most was sort of how hard it was to get the tools, like to tweak the parameters for the tools, because we didn't know what they did, and there wasn't any intuitive sense of how to get them to do what you want. And I think this is true also of commercial tools, but they come with a lot of guidance and direction. Like the manual will say, use this flag if you want to do this sort of thing, and then you get people with enough experience, so that becomes less of a problem. But yeah, I think that is still like a big gap with the open source tools. Your second question was about verification. I think verification was a big problem. We had to trust that if the design was okay through the tools and EFAB accepted it, like it passed their tests, which was just like a DRC check, then it would be okay. And then, it would be okay in some sense, but functionally, we had no way of verifying that the timing would be made at the gate level. Like we didn't know if the clock speed would be too great. We didn't know if it would work really. That is a big problem. But I think for teaching how to do and what these things do, so teaching all these steps and to teach what is necessary to get a chip to work, especially at the level of this course, this was fine. I think the next step is if you're a grad student and you want to take something out, you want to build it, you tend to spend a lot of time on verification because it matters. It's a lot of your time, you don't want to repeat it. If you're a commercial entity, then even more so, you don't want to waste time and money. The thing that makes that easier to swallow is that it's free. So it doesn't matter because someone else is paying for the shuttle. And you can do another one in a few months' time. And as long as that is true, I think we can get away with having kind of poor verification. Obviously it's not going to be the same quality or robustness or reliability of chip as something you might produce commercially, but I think it is easy enough to use today that doesn't need to be a problem for especially university courses or like field learning, right? But otherwise, yeah, I agree. We have the same issue.
Sorry, Aria, can you hear me?
Yeah.
Okay, so we have another question here. Sorry that the interaction is some kind of a little bit hiccup. So, okay. Hi Aria, thank you for a fascinating presentation. My question is not fully formed right now, so just take what you will and see what your thoughts are. Have you ever thought about how you would extend a course like this to, say, a less privileged education environment, or a completely an open environment where there's no curriculum or no payoff in the form of a course credit or even a tape out kind of product, such that someone who's kind of interested, but as you earlier mentioned, you had like a buddy system where teams would there are 2 people per team, and you also mentioned that your students had a kind of grit that they would power through problems that are or learn tickle to solve problems, things like that. If you don't have these things, or you don't have students of that much motivation, but you're faced with a less economically endowed environment, how would you bring this learning?
Yeah. So.
Thank you.
I think. Yeah, that's a good question. I think the differences with this sort of economically less well off, or like an institution, I don't know, where people don't have the same self-belief maybe to getting this done and making this useful. I think the first difference really is in the background. So we gave the students very, I think, little, and then trusted that because they made it basically to the end of their degree, they kind of figured the rest out. Like we gave them, I think they had to build some introduction, small accelerator, tweak it so that it's like it has a wider input bus or a wider output bus or something, or like even simpler designs, right? And I think there's a tremendous spectrum of designs that are very accessible, especially to people who are new to digital design, things like adders or like counters, the stuff that I like. So I learned in New Zealand, and this kind of course would have been my dream, right? If I had been given something like for free like this on the internet where I could just take like an existing design and play with it without really knowing it, then I could have let my curiosity flourish. And I would hope that that's what we could translate here. Like say I packaged this course in a way that was like, okay, we're going to try to teach you how chips are made. We're going to give you an example input, and you're going to see an example output. And then, depending on how curious you are, you can go and make the input more and more complicated, and you can try and optimize the output more and more. And that's sort of up to you, but we don't expect you to like know all of this stuff. So I think you could just do a lot more hand-holding. You could say, like, we got this design pretty dialed in, but we want you to like extend it a bit or change a bit of it and see what happens, and then you still get a flavor of, you know, what is happening and why, and what matters in the output. Like it's very exciting to me. Just it's kind of nerdy, right? Like to see GES, to see the layout. I think that's super cool. Because when I grew up and I learned about chip design, I was like, damn, this is incredible. How do we do this? And so just like I think, especially in general in education, you want to give people like little tasters of things so that they latch on to something that excites them, and then that becomes their passion, and they use that to fuel their the motivation to learn. I'm also sort of ad-libbing here. I think it's a really interesting question. I definitely think we can do it. And I think it comes down to removing assumptions about what people know and reducing the scope of what they need to do to get anything out of it, right? So as long as it's a smaller design and they can see anything in the output and they can learn something, I think that's worth doing. And of course, this stuff is free. Google hosts a lot of this in their collab environment. So you can actually run eFablets just for free on one of their like Jupyter like notebooks. And otherwise, you can run it on any old like laptop or any old computer device. It may be very slow, but like, you can still do it. So I think in many ways this is a huge step forward to making chip design accessible. We just have to get the framing right, I guess.
I see. Do we have any questions here? Okay, just come forward, because you know the camera cannot be turned around.
Hi, thank you for your presentation. Now I'm working at the EDA company. I know if EDA software have any bug, can you run it?
你可以手一个 ，OK， 这样可以，不要太近 ，OK。
Do you hear me? Okay.
Yeah.
And now I'm working at the EDA company. I know if your EDA software have any bugs, you will lose much money. So my question is, in your community, do you have someone who can help you verifying quality of software?
Yes. So that's a good question. That's a question for eFablets, really.
Yeah.
And groups that make.
Let me just explain a little bit that since our announcement of your talk, many EDA companies and fabs are considering that, the slot, the NPW shuttle is very, very expensive. How a fabless like Skywater can pay up for kind of the supposedly to be failed slots? That's a lot of money to be burned.
I think Google sponsors them. Right, so Google is providing this money to encourage the software to be built around the capability. So they've dangled this carrot, which is you get a free shuttle run if you submit to it, and you got to use our tools basically, and you got to help us build this ecosystem. And to the earlier question, yes, I think well, I've never heard of, I mean, they must exist, but typically I think the way open source community projects work is people have to check each other more than there is someone in charge of quality. I think very large projects have people in charge of quality. They have the chieftains who decide whether something is good or bad, like for example the Linux kernel. But in this case, I don't think that exists. I think it's sort of down to the developers to sort of hold themselves to some standards, and then people who are constantly checking their code because it's in the open, keep them in check as well. It's like a very different model to the commercial. So I was a professional software engineer, and we did very rigorous code review. We had product managers, we had project managers, etc., and everyone would be checking each other's work all the time, we had testers. This is not like it. This is, you're letting against people who are interested in seeing it work, making it work a tiny bit at a time. And it may be slower, but I think it works. And I think the proof is things like GCC and Linux kernel and all the other software suites we have. Yeah.
I see. Thank you a lot, because we're having 3 more minutes until another talk. So I will quick. Can you share some videos? Some audience here are asking that. Can you share your slides so they can go around and see your slides? Is it possible?
Oh yeah, sure. I will send. Yeah, I can. If you. I don't know where to send them, but I'll be able to do that.
Maybe through the email later, or.
Yeah.
Okay.
If you just send me a follow-up email, I'll just send you a reply.
I see. Okay, so.
Well, I'll just email you now, actually. I'll just email you now. Okay, well, thanks very much for having me. If there are no more questions, then that was great. Thanks for listening. Sorry, but hope I had something interesting for everyone. But yeah, if you have any questions, you can email me. I'll put my email on the slide. My emails are on the slides. Whatever you need, I'm happy to answer questions.
I see. So, yeah, thank you so much, and we'll be right here. Bye-bye. Thank you.
Bye. Thanks, Rulin. Bye.
而且因为我下一场要碰场，这个我必须要抓个8分这样子。Hi, Hugh. Can you hear me?
Hey, yeah, can you hear me?
Yeah, I can hear you perfectly. Thank you for joining us so late in the, in the States.
Yeah. Sorry, I was devoutly by the first time. Yeah.
All right. So will you be sharing the screen, or should I play the video you sent me? Is either way.
Play the video.
Video? Okay, so I will play
Yeah.
the video, and can you hold up to the live Q&A, or you? Oh,
Yeah.
Okay. Okay, so I will play the video here. Just give me a
Alright.
second.
Hey, so I'd like to present Very GPU. So what is Very GPU? Very GPU is work to create an open source GPU ASIC. So we're explicitly targeting ASIC, not FPGA. We want to do fast, it's only for machine learning, and we want to primarily use open source tooling. So what are some of the